Welcome, everyone. I am pleased to present today's session, Beyond Static Configuration, Unifying Logic and Data with Q. As our software environments become increasingly complex, the traditional methods of managing configuration often lead to errors and significant maintenance hurdles. Today, we will explore how Q moves us past these limitations by integrating logic directly with data, creating a more powerful and reliable way to define and validate our systems. Let's dive into how this unification can transform your development and deployment workflows. The configuration complexity curse represents a critical challenge in modern infrastructure management, where the tools intended to simplify our work often become the primary source of instability. At the core of this issue is the tension between serialization and configuration. While YAML and JSON are excellent for transporting data, they were never designed to handle complex infrastructure logic. By forcing these static formats to manage dynamic environments, we lose the computational power necessary for robust automation. This creates a significant validation gap. Because these formats lack native logic, errors frequently remain invisible until the moment of runtime deployment. These late-stage failures are both costly and entirely avoidable with better tooling. Furthermore, as we scale, microservices often lead to sprawl and drift. We see massive duplication across configuration files, resulting in detached abstractions that are difficult to synchronize and maintain. Finally, we must contend with fragile inheritance. When systems rely on deep layers of overrides, it becomes nearly impossible to trace the origin of a specific value. This lack of transparency turns simple updates into high-risk operations. As illustrated by the collapsing tower on this slide, when our configuration foundation is this unstable, the entire architectural integrity of the system is at risk. The Q solution provides a powerful framework for data validation and configuration management, structured around three primary pillars: configure, unify, and execute. Q is a constraint-based language that treats data validity as a first-class citizen. As a superset of JSON, backed by rigorous mathematical principles, it allows teams to define clear rules and schemas that ensure consistency across complex environments, moving beyond traditional configuration to a system that is both highly flexible and mathematically sound. The core philosophy of Q is that types are values. Rather than having a separate language for schemas and another for data, Q treats everything as part of a single spectrum of specificity. We can visualize this as a funnel where we move from the most general definitions to the most concrete. At the top of this hierarchy is top, represented by an underscore, which encompasses every possible value. As we move down the funnel, we add specificity. Kinds, such as strings or integers, narrow the field. Constraints, such as greater than 10, refine it further. Finally, we reach concrete values, like the number 5, which represent the most specific points on the spectrum. In this model, validation is simply the intersection of these values. If two constraints contradict each other, for example, if we require a value to be greater than 10, but then provide the concrete value of 5, the result is pushed to the very tip of the funnel, bottom. Bottom represents an error or an unsatisfiable state, signifying that the combined constraints are logically impossible. The power of unification lies in its mathematical consistency. As the equation A and B equals B and A demonstrates, order is irrelevant. This commutativity represents a fundamental shift in how we approach configuration management. Unlike traditional systems where the sequence of operations determines the final state, unification treats all declarations as simultaneous, converging constraints. The first key principle to understand is refinement, not override. In this model, you cannot change a concrete value once it has been established. You can only provide additional details to make it more specific. This leads to a significant practical benefit. Configuration can be split across multiple files, modules, or environments without ever worrying about load order. The final result will remain identical regardless of which part is processed first. Looking at the code example, we see a valid unification at work. We initially define a constraint stating that the port must be greater than 1000. When we later define the port as 8080, the system evaluates both requirements together. Since 8080 satisfies the original constraint, the value is successfully refined, resulting in a final, concrete output of 8080. This approach ensures that our configurations are both flexible and inherently safe. Validation is a cornerstone of the shift-left strategy, aiming to identify issues as early as possible in the software delivery pipeline. By leveraging Q, we can define structured rules to ensure configuration consistency across our environments. In this example, we define a schema called #spec that requires the resource kind to be a deployment and mandates a minimum replica count of 2. A significant advantage of this approach is the ability to validate data without needing to modify the original source files. By using the Q-vet command, we can check our YAML manifests against these rules locally, catching potential configuration errors before they ever reach a production cluster. Let's explore the concept of closedness in Q schema definitions. In Q, definitions, prefixed with a hash symbol, like #service, represent what are called closed structs. A key differentiator from JSON schema is that these definitions forbid unknown fields by default. Take a look at the code example provided. We define a #service that requires a port field of type integer. When we attempt to create a configuration by unifying #service with a new struct, even a simple typo like prot instead of port will be caught immediately. Q will return an error stating that the field is not allowed. This strictness is incredibly powerful for maintaining data integrity and catching configuration errors before they ever reach production. Reducing boilerplate is a fundamental goal of the DRY principle. Don't repeat yourself. On the left, we see the typical before state using YAML, where large-scale configurations often result in a messy, overwhelming stack of files filled with redundant data. By transitioning to Q, as shown on the right, we can transform that clutter into a streamlined and organized structure. A powerful tool in this process is the Q trim command. This command automatically removes data from your files if that information is already implied by the schema or existing defaults. This ensures your configuration remains as concise as possible, significantly lowering the maintenance burden by eliminating unnecessary repetition. Templating and dynamic configuration allow us to maintain high levels of consistency across large datasets. Specifically, pattern constraints enabled an enforcement of rules across dynamic lists or maps. In the code example shown, we first define that every entry in the services map must conform to the #service schema. We can then go a step further by using pattern constraints to inject data dynamically. By capturing the map key using the bracketed name =_ syntax, we can automatically assign that key to a name field within the nested struct. This approach eliminates the need for manual repetition and ensures that resource identifiers are always synchronized with their internal configurations. Much like a physical stamp, these constraints allow us to apply uniform logic across all elements in a collection, regardless of how many entries it contains. The integration between Kubernetes and Q follows a streamlined 3-step workflow designed to enhance configuration management. It begins with the import phase, where the command q-import allows you to ingest existing Kubernetes YAML or JSON files into the Q ecosystem. Once imported, we move to the define stage. Here, you apply schemas from the Q registry to enforce consistency, validate data types, and define complex relationships within your configuration. Finally, the process concludes with the generate phase. Using Q export, Q compiles these definitions back into a standard manifest.yaml file. This approach ensures that your Kubernetes manifests are not only generated automatically, but are also fully validated against your defined schemas before deployment. The concept of Q as the interlingua of configuration highlights its unique role as a central hub for modern infrastructure and application management. At its core, Q is designed to bridge the functional gaps between code, data, and specifications. As illustrated, Q provides bidirectional compatibility with common data formats like JSON and YAML, allowing for seamless translation and rigorous validation of configuration files. It extends this capability to interface specifications such as OpenAPI and Protobuf, ensuring consistency between API definitions and their underlying data models. Furthermore, Q integrates directly with programming languages like Go, creating a unified source of truth. By acting as this universal bridge, Q enables teams to maintain high standards of type safety and validation while moving fluidly between different layers of their technology stack. Policy as code and governance provides the necessary guardrails to manage our infrastructure and deployment processes automatically. By codifying our rules, we can validate GitHub Actions and GitLab CI pipelines before they are executed. This ensures strict compliance across the board, such as mandating the use of specific trusted image registries and preventing invalid configurations from being deployed. As shown in the code snippet, we can define precise logic, for example, requiring a minimum of 3 replicas for any production environment. This programmatic approach eliminates manual oversight, reduces risk, and ensures that our governance standards are consistently applied throughout the software development lifecycle. In this technical summary, we examine why Q is the leading choice for configuration management. First, it is hermetic, providing deterministic output every time to ensure consistency across all environments. Second, it is highly scalable. Complexity is managed through integrated logic rather than manual text editing, allowing your configurations to grow without overhead. Third, Q is safe by design. Types and values are unified, which means errors are caught early in the development cycle. Finally, it is interoperable, working seamlessly with the tools and ecosystems you already use. Together, these pillars make Q a robust and reliable solution for modern technical needs. To begin your journey with Q, we follow a structured 4-step process designed to transition existing configurations seamlessly. The first step is validate, where we utilize the Q vet command to verify existing YAML files against Q constraints. This allows for immediate quality assurance without altering your underlying data. Next, we transition to the import phase. Using Q import, you can migrate your current configurations directly into the Q ecosystem, converting them into structured, manageable code. Once imported, we move to the refine stage. By applying Q trim, you can automatically remove redundancies and boilerplate, resulting in a cleaner and more efficient codebase. The final objective is to automate. By integrating Q into your CI/CD pipelines, you ensure continuous validation and streamline your deployment workflows. You can find further documentation at qlang.org and test these features directly in the Q Playground. To achieve meaningful results, we must first fix the foundation. For too long, the focus has been on managing strings, disconnected pieces of text and unstructured data that often lead to complexity and confusion. Our goal is to shift that paradigm and move toward managing truth. By establishing a grounded, reliable source of information, we ensure that every insight is anchored in accuracy, providing a stable base upon which we can build more effective and intelligent systems.